Hello guys, welcome to my channel. In this class we're going to consider the concept of surds, and we're basically going to look at the subtopics: definition of surd, the types of surd, rules of surd, and simplification of surds. And subsequently we'll look at basic operations involving surds. We'll look at surd rationalization, radical equations, and other things. Okay, so now straight away, what is a surd? Now you remember that when we talked about types of numbers, we said that we have what we call the rational numbers, or what we call the rational numbers, and now we have what we call the irrational numbers. Now these are two major types of numbers. Now we saw that rational numbers are numbers that can be expressed as fractions of whole numbers. That means stuff like whole numbers themselves, because if you have 2 can be written as 2 over 1, so that means it's expressible as a fraction of integers. And then so other fractions, that are fractions of integers. Now while irrational numbers are numbers that can be expressed as fractions of integers, so when they are in decimal form, they do not terminate and they do not repeat digits. So such as examples such as pi is an irrational number, e, which is the Euler number, and all irrational roots are all irrational numbers, root 2, root 3, and so on and so forth. So now, why did I call this irrational roots? Because we have rational roots. Example, if I give you something like root 4, you discover that root 4 is equal to 2, so it gives you a rational number. And other examples, root 9, root 16, the root of any perfect square is a rational root, and it gives you a rational number. Okay, so now we discovered that the irrational roots are all examples of irrational numbers, but not all irrational numbers are surds. So now all of these irrational roots are what we call surds. Like my definition here, I said a surd is an expression that contains one or more irrational roots. So when any expression contains any of these irrational roots, like root 2 or root 3, we refer to that expression as a surd. So you can see other examples of surds. Right, so you can see other examples of surds, such as numbers like 1 plus root 10 is a surd. Something like 3 minus 5 root 2 is a surd, and so on. Okay, so now when an expression, even though this one now contains a rational number, however inside it you have the irrational root, and so you call the whole of this number, this whole of this expression, an irrational number, which is a surd. Okay, and the same is applicable to this. Okay, so having seen the definition of surds, quickly we are going to look at the types of surds. And from my list here, you can see I have already listed the types of surds, and so we are beginning with pure surds. So now, before we get to types of surds, remember that every surd is of the form A root B. Every surd is of this form. There is always the rational part, and there is always the irrational part. A is called the rational part, while the root B is called the irrational part. Remember that this root is called the radical, while this B, the number under the root, is called the radicand. Okay, so now so when you have a single surd like root 2, for instance, so one will be asking, what is the value of A? Of course, you know that A is the coefficient of root 2 here, which is 1, and in this case our B is 2. Okay, quickly let's go to types of surds. So we begin with the pure surds. So we see that a pure surd is a surd that contains only the irrational terms, they contain only, you know, the numbers with the radicals. So example, we already talked about root 2. This is an example of a pure surd, and this guy is also an example of a pure surd, root 3. And you can have other examples like, say, root 5 plus root 6. This is also an example of a pure surd. Now, but if we have in any expression that is a surd the presence of a rational term, you refer to that surd as a mixed surd. Examples of mixed surds, so here we have stuff like this guy now is a mixed surd, and this person also now is also a mixed surd, because there is the presence of a rational term. There is the presence of a rational term, and so once there is the presence of a rational term in a surd, you call that surd a mixed surd. Okay, so we have examples of mixed surd. The two of these are examples, and there are other examples. And so quickly we look at the next type of surd, that's the basic surds. So we have the basic surds. The basic surds are also called simple surds. So these are surds that cannot be further reduced into any simpler form. Now, and why is this so? It is so because the radicands, that's the number under their radicals, cannot be expressed as multiples of perfect square. For example, when you have root 3 is a pure example of a basic surd. I can't reduce this surd to any simpler form because the 3 here cannot be expressed as a multiple of a perfect square. You can't write 3 as a multiple of a perfect square. And you have other examples. For example, 2 base 5 is in its simplest form now. And there are other examples, root 7, 2 root 5, sorry, root 7 now, root 11, and so on and so forth. Now, but when you have a surd, for example, root 8, where the number, the radicand, can be expressed as a multiple of a perfect square. For example, we know that 8 can be written as 4 times 2, where 4 is a perfect square. So you see that this surd now, we can further reduce this surd into a simpler form. And if I do that, I am going to get 2 root 2. So surds of this form are called compound surds. They are called compound surds. Another name is complex surds. Okay, and so we have many examples of that. Root 18 is a compound surd, root 27 is a compound surd, root 24, and root, many of them, 54 is a compound surd, and so on and so forth. There are many. So first you can express the number as a product of a perfect square and another number. So you say that that's all. Like now 54 can be written as 9 times 6, and 9 is a perfect square. So, and of course, if I now reduce this, I'm going to get 3 root 6, and that gives me the simplest form of it. So now quickly we go to the next one, that is the similar surds. So what are similar surds? So we say that similar surds are surds that contain the same number as radicands. So if I have something like A root B and C root B, the radicands are the same. So you refer to these two surds as similar surds. And so you can give yourself many examples. For instance, root 3 and let's say 5 root 3 are similar surds because their radicands are equal. Okay, and that is similar surds. So we go for equality of surds. For equality of surds, two surds, if you have surd A root B and C say root D, these two surds are only equal. They are only equal if and only if A is equal to C and B is equal to D. So the rational part must be equal and the irrational part must be equal. So your A must be equal to this C, and your B here, which is the irrational, the radicand, must be equal to the radicand of this one. If that doesn't happen, then they are not equal. And you can see examples on this. So one of it is that one can say if, say, B root 3 is equal to 7 root 3, find the value of B. It's very easy. Find the, so of course you can see by equality of sort, since their irrational parts are the same, that means their irrational part must also be the same. Therefore our b here is equal to 7. And we can also apply equality of sorts when we talk about the square root of sorts, and we are going to see that in our further lessons. So the next thing we are going to talk about now is conjugate. Right, so conjugate sorts are the other types of sorts that we're going to look at. Okay, so when are sorts said to be conjugate? When we're talking about conjugate sorts, we are referring to two sorts, just like you have in similar sorts and equal sorts. You're talking about similar sorts, you're referring to two sorts. Two sorts can be similar when something happens. The same thing with equality of sorts, and the same thing with conjugate sorts. So conjugate sorts is with regards to two sorts. So two sorts are said to be conjugate when their product leads to a rational number. So if I have a sort, say root a times root b, and the product gives me a rational number. Remember, the product is going to be root a times b. Of course, we are going to see this under the rules of sorts. Okay, so if their product gives us a rational number, then we refer to the two sorts as conjugate pairs, or you can say conjugate sorts, or you can say one is a conjugate of the other. Right. Okay, so now there are two basic ways to identify the conjugate of sorts. The first one is whenever you have a basic sort, every basic sort is a conjugate of itself. Every basic sort is a conjugate. Sorry. So every basic sort is a conjugate of itself. So example, root 2 is a conjugate of itself because root 2 times root 2 by the multiplication I just showed above is going to give you root 4, and root 4 is equal to 2. So that gives you a rational number. Any other conjugate, any other basic sort you pick, say 3 root 5. Now I can multiply this by 3 root 5, which is itself, or even just root 5. Any of it will still give you a conjugate. So if I multiply by itself, which is 3 root 5, I'm going to get this number here will multiply this to give me 9, and this root will multiply this root to give me root 25. And root 25 is 5. 5 times 9 will give us what? 45. Okay, so you see that every basic sort is a conjugate of itself. Okay, so quickly we go to the next way or next type of conjugates. How do you get the conjugate? So if you don't have a basic sort and you have a pure sort like this, say root a plus root b, if it is addition, the conjugate of this is simply the subtraction. Just take the difference of this and that will give you the conjugate. So remember that this is also a pure sort. Assuming what you have is a mixed sort, let's say a number, a constant, let's say a plus root b. The same thing happens. The conjugate of this is also a minus root b. Okay, so if it is minus, the conjugate becomes plus. If it is plus, the conjugate becomes minus. And you can see that this comes from the general and basic principle of difference of two squares. You know that if you multiply a plus root b by a minus root b, you are going to get, the expansion of a difference of two squares, which is the same thing as a squared, minus, a squared minus a squared minus, you're going to get minus square root of b all squared. And of course, you know that this is going to give you a squared minus the square of this will be b. And since a squared is rational and b is rational, the difference of rational numbers will give you what? A rational number. Okay, so that's how to, that's the meaning of conjugate sorts. Okay, so having seen all the types of sorts that we are going to consider, the next is to look at the rules of sort. And I'm going to do that over here quickly. So what are the rules of surds? So the rules of surds includes the following. The first one here says, I've already stated that up here. So it says that if I have root A multiplying root B, that this is the same thing as root A times B. Okay. The second one, if I have root A all over root B, that this is the same thing as take one of the roots and divide the numbers under the roots. Okay. And so now in general, assuming like what I did here, assuming there is a coefficient, let's say each of them they have coefficients. So let's take it that you have A root B times C root D. This is going to simply give you the coefficients to multiply, and so you have AC, then you take one of the roots, then multiply the radicands, and that will give you BD. Okay, so these are the two basic rules of surd. And now the other ones are just remarks, which I'm going to let us see. So let's see these remarks. These remarks here, very important remarks. Okay, the first remark here says that the thing that holds for multiplication and division doesn't hold for addition and subtraction. That's just the remark. That means root A plus root B is not equal to, root A plus B. Please take note of that. And then the second one is for subtraction. Root A minus root B is not equal to root A minus B. And then another very important remark we should note is that assuming that we have, let me clean here. So assuming that we have, let me call it number 3 now. So let's take it that we have root A times root A. This is going to give you what? A. I've already mentioned that under, the conjugate of basic surds. So please take note of that. So whenever you have the root of anything, multiply by the root of that same thing, you will get the radicand under the root. So these are the basic rules of surds that we have. The next thing we're going to look at now is simplification of surds. So in continuation, we are going to consider simplification of surds. And so what is simplification of surds all about? So we see that to simplify a surd, there are two things that we can actually be required of. One is to reduce the surd to basic form. And we have discussed basic surds here. So you should already know what a basic surd is, meaning the surd that will be given to you will probably be a complex or a compound surd, and you are required to reduce it to the basic form. That's the simplest form. And then the second part of it is expressing a surd as a single surd. That's the opposite direction. Maybe the surd is already in a basic form and it is having a coefficient, and so you are asked to required to change it into a single surd. So this is just the opposite or reverse of each other. So what do we do? So quickly, we have example here. One says reduce the following surds to basic form. So we start with the first one here. So we have root 27. So what do we do? Remember I said that a basic surd, a compound surd, is a surd that you can express its radicand as multiple of a perfect square. So that's what is going to guide us here. So we are going to look for the perfect square contained in this number. And so is there any perfect square in 27? Yes, that is what? 9. So I have 9 times 3 now will give me 27. And by rule of surd, I can split this into root 9 times root 3. And when that happens, what is root 9? Root 9 is simply 3. And what is my root 3? Of course, I can't express that one. So when you multiply these two, you are going to have 3 root 3. And that is your answer. Okay, so that's how to reduce a surd into a basic form. We go to the second one. What's the perfect square in this? And so quickly, we can see that the perfect square here is 36. So I can quickly take 36 by 2, and that will give me what I'm looking for. And so what is 36
times 2, that's 72. So I can split it as well. So now instead of you going through the stress of splitting all this way, immediately you get this product that you're looking for, just take the square root of the perfect square and bring it out of the root, and then write the other one remaining, and that is just your answer. So the square root of 36 is 6, so I'll just bring it out, and then I'll have times this root of 2, and that's my answer. And finally, for the example here, we have, I can split this into 9 times 6, and that will give me 54. So the square root of 9 is 3, and so I'll just bring it out, and that will give me 3 to the root of 6, and that's the solution to that problem. Okay, right. So for this other one, example 2, now we have, write the following as single surds. So what do we do here? To write these surds as single surds, the opposite of what we have done in this place is what we're going to do here. So the implication is that the root of this number was taken before it came out of this square root. So if I want to bring it back into the square root so that I can have a single surd, all I need to do is to square it. When I square it, then I'll bring it into the square root. And so when you do that, that's going to give us the square root of, if you square 5, you get 25. And of course, when it comes into the square root, it will multiply the number that is already there. And that's going to give us 25 times 5, which is 125. And that's the single root you're looking for, single surd. And so what about the second example? The second example is going to, now lead us also into one of the rules of surds that we discussed here. And what is that rule? The rule of division. So what should I do here so that I'll be able to get one surd that I'm looking for? Now I'm also going to know that for this 3 here to become a rational number, the square root was taken. So I'm going to bring back the square root by squaring this. And if I do that, I'm going to get the root of 9 all over the root of 3. And so by the rule of surds, when you have two roots or two surds dividing, I can simply take one root, and that's 9 over 3. And the root of 9 over 3 is simply the root of 3. And that's your answer. And then you will do the same for this. This is root 6 all over. For you to have 12, it means the square root was taken, and that's the square root of 144. And that's going to give us, we take one root now, 6 all over 144. And you try to reduce it to the lowest term. And when you do that, if 2 divide 6, you get 3. Divide this, you get 72. And 3 can divide 72 to give us 24. So you are going to have 1 all over 24 as your single root. And so that's the solution to these problems. And this is all about a simplification of surds. Okay, and that's where we will end it for this class. In our subsequent classes, we are going to look at basic operations in surds such as addition, subtraction, and so on and so forth. Thank you for checking our videos, and subscribe please if you have not subscribed, and click the thumbs up. We'll see you in our next class. Please do have a nice day. Thank you for watching.